Hey everybody, Chris here. Before we start this episode of Syzygy, I just wanted to say, yeah, I know, we've been a bit slow on this one. We recorded this way back towards the beginning of December, before Emily headed off to New Zealand, before Christmas, before New Year. Now it's suddenly the middle of January? How did that happen? But listen, it's been a big year. It's been a tough year for all sorts of people. We count ourselves pretty lucky that we've been able to just sort of, shelter indoors and record a podcast every once in a while. But I know that a lot of people have been hurting a lot more than that. For us, it's really just been about a delayed podcast schedule. So stick around. We are going to continue recording Syzygy. We are still committed to this thing, and we love the fact that you're tuning in. Thanks very much for your support. I also wanted to say that if you do enjoy the show, then there's another show you might be interested in as well. It's not astronomy-based, but it is mostly about science. It's a new show that I've started with a friend of both Emily's and mine, a guy called James Lees. He's another science communicator, where we tell each other stories which are, if not scientific, at least science adjacent. It's called Science Possibly, and you can go and catch it at sciencepossibly.com or just search for it on your podcast catcher of choice. Anyway, enough of all of that. Thanks for listening. Cue the theme music. Syzygy, episode 74, Vale Arecibo. Hello and welcome back for another edition of the Syzygy podcast. Joining me from across the other side of the country, because we're still in socially distanced mode, Emily Brunsden. Hi Emily, how you doing?
Hello. Feeling a bit melancholy today.
Yeah.
Got to be said.
Yeah, look, the entire episode is devoted to those melancholy feelings. So we'll get back to that in just a second. But just as long as you're okay, you're doing all right.
I'm fine, yeah.
Yeah. And I mean, more than fine, you're about to get on a plane. I think in the last episode, I forecast that the next episode, which would be this episode, was going to be talking to you from the opposite ends of the earth. But we're not quite there yet. You haven't yet got on a plane. But remind us again, where are you going?
I'm fortunate enough to be able to head back to New Zealand to see my family, etc. But fingers crossed, all going well, I might be able to get down to some telescopes and do some observing there as well.
That would be cool. But of course, New Zealand has its long quarantine period still going on. So you're going to be spending Christmas in a quarantine hotel, which is fun. Yay. So everyone send your best Christmas wishes to Emily, care of the quarantine hotel, probably somewhere near Auckland, Wellington, I don't know. Somewhere. Down in New Zealand. Yeah.
Who knows?
Wherever they fling you.
It's like
in
a
the
mystery
bus from the
holiday
airport.
where the mystery is which hotel you get to go to.
That's a really rubbish mystery holiday. Pick a hotel, stay here for the next 2 weeks, including Christmas. Anyway, well, good luck with the trip when you do go. Before we get onto the theme of today, the melancholy theme of today, a couple of bits of news from the last week. We've had a Chinese spacecraft landing on the moon, ready to bring some stuff back. And we've had a Japanese spacecraft bringing some stuff back from the place that it did land a while ago. Emily, what's going on?
Yeah, so, two very, very successful seek and return missions, which is really exciting because this is the kind of stuff that we've struggled with in the past, let's be honest. China getting some samples, has left the moon, has returned. I mean, it's all happened so quickly. You sort of forget that the moon's quite close. So I think I'm used to thinking about planetary missions, asteroid missions, etc. You've got to wait years and years for these things to happen. Yeah,
at least months, if not many, many years. And then the moon's just up there. It's a couple of days. And if you're a human being in a small tin can flinging your way there, that's a really long way. But in terms of sending, a hunk of computerized metal up there to do its thing, it's not so far. Although the whole landing, taking samples, and then in particular sending them back home again, that's not easy. That's the really hard part.
Absolutely not. I mean, we've seen and talked about several failed missions because of various just difficulties, right?
Yeah, as they say, it's not the fall, it's the stopping at the end that is particularly hard. But this one's been successful. Has the Chinese mission, has that got its sample and started the return journey yet, or are they still there?
That's a good question. I haven't caught up. The internet will tell us.
I'm sure it will.
So it set off on the 3rd of December, so a few days ago. Docked on lunar orbit on the 5th, and undocking of the ascender from the orbiter returner combination lock on the 6th. So it must be just about to be back.
Yeah, we're recording this on Tuesday, the 8th of December, and so Emily's real-time research there.
Yes.
Look, I'm going to say right at this exact moment in time, we may well be mid-mission, in which case by the time you're listening to this, you will know, dear listener, whether or not the samples have in fact returned from the moon safely. So good luck to what was the name of that mission again? It was the
Chang'e 5.
Chang'e 5. Well, good luck, Chang'e 5. Come on, do the thing. And Hayabusa has actually done its thing. It's back now.
Absolutely, yeah. So that was quite cool. Crash landing went exceptionally well. You might remember when we did a little episode about Hayabusa 1. We talked about Hayabusa 2 and what it was up to, because it had just sort of arrived at its asteroid. But the first mission in this sort of series, they had the sample, they got it all the way back to Earth, but it crashed into the Australian desert, and the sort of container was compromised at that point, so it was a bit contaminated.
Yeah, to go all of that way and then to intentionally crash into the Australian desert. I mean, Australia's got a lot of desert, we may as well use it. But for that to then, compromise the entire purpose of the mission is sad. And on this occasion?
Total success, absolute success. Apparently it's in perfect condition.
Hurrah.
They've done some quick tests after picking it up in Australia again, but it's now on its way back to Japan, and it's going to be sort of deeply investigated, I guess, over the coming months and years.
Brilliant. Well done, all involved. Very exciting. Well, listen, let's get on to the topic of the day, which, as you said in your introduction, Emily, is a bit melancholy. It's a bit sad. What's been going on? What's bringing you down?
Well, we've had some pretty gut-wrenching video footage, I guess, released over the last few days of the complete and utter devastating destruction of the Arecibo Radio Telescope in Puerto Rico. Yeah,
we'll put a link to that video in the show notes. The Arecibo, for those of you who aren't familiar, is the enormous radio dish set into what I've only just found out was actually a bit of a sinkhole down there in Puerto Rico. But how wide is this thing? It's enormous.
So it's 305 meters.
305 meters, which is enormous by anyone's measure. That's a huge, huge thing. Set into the ground itself. And it's been there for how long? Decades, right?
About 57 years.
Wow.
So it's a real classic.
Such an icon of astronomy. Except that it's kind of fallen apart, hasn't it?
It has, and it was such a dramatic and devastating sort of falling apart. So, I mean, for those of you who've been sort of following Arecibo over the last few years, it's not had a great time of it, let's be honest, over the last sort of 5 years or so. You may remember in the news in 2017, Hurricane Maria actually caused quite a lot of damage to the telescope, which was repaired. But, that was a bit of a blow. And between then and now, the National Science Foundation, which is the US kind of funding agency that looks after it, has been kind of cutting funding to the telescope. And then there was some sort of more damage in August this year. Some cables broke, and it was sort of on the way down, if you like. The NSF announced just last month that it was going to be decommissioned, the whole telescope, and they were going to do kind of an environmental impact study to pull it all apart and take it all down. But they didn't get a chance, because just a few days later, one of the, or several of the cables holding up the central sort of structure in the dish just broke, and the whole thing just came crashing down into the dish.
And that's a sizable chunk of stuff, right? I mean, that strung up above this enormous dish was presumably a lot of electronics and so on as a receiver for the radio waves bouncing off the dish up to an enormous receiver, which itself would have been pretty hefty. And so to have that crashing down...
820 tons crashing down 150 meters into the dish.
That's a lot of potential energy right there. That's really going to do some damage. See, here's the thing, Emily. I'm quite embarrassed to admit this. When I saw that all of this damage was happening and clicked through to a bunch of the images, for the first time, I realized how this telescope had been constructed, because in my mind, having seen the pictures, which are usually taken from a bit of a distance, right, so that you can see the whole curve of the dish, right? In my mind, it was basically an enormous skateboard ramp. I think I had in my head that they had hollowed out the side of this, or the top of this hill, and lined it, and it's stupid saying it now, lined it with concrete or something. You know, that's what I've got in my head, is this enormous, because that's what it looks like. And what do I know about telescopes other than the fact that, you know, I studied physics for far too many years and I should have known better. But in my head, this was an enormous, let's call it concrete structure with a big thing above it. And so when I started to hear about how much it was damaged and falling apart, a little bit of my brain went, but how, I mean, couldn't they just sort of, you know, smooth a bit more concrete over? No, Chris, it's not made of concrete, is it? Is it,
no,
Emily?
because it turns out concrete's not particularly reflective to radio waves.
No, it's a bit rubbish for reflecting radio waves. Might be all right for reflecting sound, but not radio waves. So how is this thing constructed?
So it's constructed actually pretty similar to the classic radio telescope that we have on the Astro campus, which you will be familiar with.
Yeah. It should have been a giveaway, really, shouldn't it?
Yeah, similar sort of thing. It's a metal mesh, an aluminium mesh, because you don't need to have a mirror like you have for optical astronomy. And for the light that we see, if you want to reflect the light that we see, you need to have something that's incredibly reflective and shiny, like a mirror. So that's really like high polished aluminium surfaces, but that's because the wavelength of the light that we see is incredibly tiny, so you've got to have this really nice, smooth, shiny surface. But when you're talking about radio waves, I mean, if you want to catch a radio wave, which is kind of a few centimeters or a meter in size, you don't have to be that smooth and shiny, fortunately.
No, I mean, smooth and shiny at the level of radio waves is bumps on the order of what sort of centimeters to feet, or centimeters to meters long. And that's perfectly smooth as far as it's concerned. So this is a mirror just for radio waves.
Yeah, so it means that you can build things like mesh, which of course are lighter, they're sort of more easy to keep stable mechanically. And in terms of the Arecibo dish, you can actually grow plants underneath them because they're just a little bit shady.
Yeah, nice. And I should have known all of that, and that does make a hell of a lot of sense. But in my mind, the skateboard ramp just... I mean, look, that would be great fun if they could... A little bit like in the movie The Dish. Have you seen that? The great Samuel
where they play
film,
cricket.
where they play cricket on the Parkes telescope. I reckon having a good old skateboard on Arecibo would be terrific. But I imagine that's probably not the thing. Anyway, it really, really has had not a great month, hasn't it? So is it completely gone now? Is it sort of...
Yeah.
There's no rescuing this now,
There's
is there?
no coming back from this.
No.
I mean, it's so... I think what the part of the emotional sort of grippingness of it is it's the sheer drama of the entire thing. If you watch the video, you see the sort of the rope snap, and then you see the whole thing just go plummeting down, causing immense amount of destruction in the disc. It kind of rips apart the frame. The towers that sort of hold up the receiver, suspended from three big towers. You know, the whole tops of the towers come crashing into the dish. There's dust and things going everywhere.
I mean, if you're going to go, you may as well go in style, right?
It's horrifying. You know, the sort of thing that you can take away that's positive, I guess, from the whole thing is that thankfully the whole facility was shut down for safety and there was nobody even remotely near it.
Yeah, I mean, those cables flinging around and bits of, you know, telescope mesh being knocked by, as we said, 800 tons worth of stuff collapsing down onto it. You don't want to be anywhere in the vicinity of this thing. But as you say, it's been... the funding has been decreasing for the best part of 2 decades now. That it was funded by the American National Science Foundation, I think, in the main.
Yep.
And I think they kind of saw the writing on the wall back in the mid-2000s that it's getting old. It might be better to throw our funds somewhere else, I think was the justification. But it did mean that over time, obviously, this particular facility, when it got damaged by you know, big storms and stuff like that, there just wasn't the funds to do it back up and keep it running, which is, as you say, it's a real shame. So can we talk a little bit about what was the science of this thing? What was Arecibo like? I know it as an icon of astronomy, but I'm really hard pressed to know, what was Arecibo for? What did it do?
So amazingly, Arecibo was the world's largest single aperture telescope for 53 years.
That's a hell of a record.
Yeah, it's amazing. And, it's one of these things that it's got lots of awards for sort of engineering milestones and so on. So you can imagine that the technology that went into this was incredible. And of course, over the 57 years of its observing history, it's provided massive amounts of stuff. Like, you wouldn't, it's hard to underestimate, it's hard to overstate just how much of our modern astronomical knowledge is based on partially stuff that's come from Arecibo. I mean, you take just something as simple as landing on the moon. Hey, the radar mapping that was done to choose the landing site for the Apollo missions, done from Arecibo. The Viking explorers on Mars, similar thing. The mapping of Mars was done by Arecibo to choose their landing locations.
Because if you're going back 57-ish years, you're going into the mid-60s, right, when this thing would have properly come online.
63, yeah.
And so that's prime. We're off exploring the solar system at that point, in which case you really need some good telescopes to show you where you're going.
Yeah, and it's amazing facility. So it was actually kind of envisaged, not really even as an astronomical telescope.
Oh, really?
It was actually sort of dreamt up as more something to look at atmospheric science. So looking at the ionosphere, which is kind of the upper atmosphere, looking at reflecting waves off the ionosphere to measure changes in that sort of structure. But as it was being proposed, some sort of people came along and said, well, hang on, you're doing this.
If you're going to go to all this trouble,
just add a few little tweaks here and here, or hey, we can use this for radio astronomy as well. And of course, radio astronomy was taken off in the 60s. We just sort of put together the technology to build big radio telescopes. So it was this nice combination, and this combination of sort of being set up as a high energy transmitter. So this is a radar transmitter. So it means it's putting out radar light, so that it can bounce it off surfaces, catch it back again, and measure the changes. Okay.
So it can receive and send.
So it can receive and send, which was something very, very unique. And in fact, until just a few days ago, it was one of only 2 observatories in the world that could do this.
Really? What's the other one?
And so the other one's actually a 70-meter dish in the US, so much, much smaller, and is sort of, from what I can briefly look at, it's mostly used for military purposes, so the astronomical time on it's fairly limited.
Wow, I'm not sure that I'd entirely appreciated that about the receiving and sending part. So, okay, let's have a talk about the astronomical side. What would you say would be, the big highlights of Arecibo's history, 50-plus year history?
Well, this is just the amazing thing. I sort of went through, so it does research in radio astronomy, radar astronomy, SETI. We'll come back to SETI, I think, but that's... search for extraterrestrial intelligence, near-Earth objects, so tracking sort of rocks that come to us. I've sort of made a very quick list, and it started to grow pretty quickly, so I had to sort of cull it down a little bit. But here are some of, I guess, the really kind of important discoveries that Arecibo, just on its own, made.
Okay.
So going back to even just 1 year after opening, so 1964, it was discovered that the rotation period of Mercury was 59 days. Mm-hmm. When at the time we thought it was 88 days, the same as its orbital period, but that was quite a revelation to find out actually Mercury's spinning a whole lot quicker on its axis. So even something simple as just the rotational period of a planet in our solar system.
And that was one of its first successes.
Yeah, amazingly. If you think about probably the most famous pulsar that we know, which is the Crab pulsar. This is a pulsating neutron star which is hidden deep within the Crab Nebula, one of the most famous supernova remnants that we can see in the sky.
Yeah, so iconic.
Yeah. So that was discovered to have this 33 millisecond period. And this was this is 68, and that was proof that neutron stars, these kind of very compact neutron stars and pulsars exist. Going forward to 74, the first binary pulsar was discovered in Arecibo, getting a Nobel Prize later on for that discovery.
Oh, yeah, that's right. Yeah, so that was through Arecibo. Cool.
Yeah. 82, the first millisecond pulsar. So this is pulsars that spin and that go around at enormous rotation periods. So in this case, it was spinning 642 times per second.
Yeah, I mean, we've talked about pulsars on a number of times on this show, and it still never fails to boggle the mind that something, I mean, pulsars, neutrons are very, very compact things, but they're still pretty big. They're not tiny objects.
Absolutely not. They're sort of planet size.
And for it to be spinning at that kind of rate is just bonkers. That's utterly insane.
Yeah, so I mean, if you want to know more about pulsars, then flick back to episode 66, where we did a really, really nice look at pulsars, including millisecond pulsars as well.
Yeah, that's
these
right.
Really fast ones.
Episode 66, Inscrutable Neutrons and Perplexing Pulsars. That was the one. Cool. Okay, so it's done a lot of pulsar stuff.
So in 89, we had the first direct image of an asteroid, which...
Wow, okay.
Yeah, that's amazing, isn't it? You think... We should have gone and sent Voyager probes and photographed asteroids and things like that.
Okay, hang on a second. But it's a radio telescope.
Yeah.
How are you getting a direct image of an asteroid with a radio telescope? That doesn't make any sense to me, Emily. What's going on?
So this is a big part of Arecibo's speciality, is this radar mapping. So what it does is it sends out the radar signals, really, really high energy radar. And you think about radar, you think about the technology kind of from World War II or something like that, where you've got little blips that you are coming up on a sort of a green computer screen with a little compass needle going around.
We know there's an airship over the horizon. It's a blip on our radar screen. Yeah.
Beep. I mean, it's fundamentally the same sort of idea, except you send out a whole lot of you send out a beam of radar, and then when that beam comes back to you, you look at how that beam has been distorted by reflecting off the surface of the object that it's reflected off.
Are you serious? That's extraordinary that it's sending out. So from this enormous dish, you were sending out this beam of radar, of radio waves, bouncing off an asteroid, and you can, from the detail of that you then pick up with the same dish, you can tell what the asteroid looks like? That's nuts.
It's so cool, isn't it?
Wow, and that was in 89.
But you do need to have, a fairly big old telescope with a very, very high-powered radar system in it.
Well, turns out that's what they had, so well done.
Okay, here's another one that you have probably heard of. In 1990, the first discovery of exoplanets.
Yes, again, we've talked about this before on the podcast, but the first one was with Arecibo.
With Arecibo, which we sometimes I can skip over and forget sometimes. I know we're very sentient to it because I talk about it all the time. But as kind of astronomers or people interested in astronomy, you imagine the first exoplanet that we found. We talk about 1995 very often because that was when the first planets were found around what we call like an ordinary star.
Right.
And this is what the Nobel Prize was for. But actually, before that, 5 years before that, we detected these objects, which we now know to be exoplanets, around pulsars, very extreme, very weird objects.
Is that why it was detected with Arecibo, in a sense, is that Arecibo was really good at finding pulsars, and therefore it would also be pretty good at noticing that there's something odd with this pulsar signal? Is that the idea? Because pulsars are incredibly regular. That's one of the things about pulsars. So I'm guessing you've got an incredibly regular pulsar, which is occasionally not so regular, and that's a sign that there's something going around it?
Yeah, exactly. So if you've only got planets going around a pulsar, briefly the timing of the pulsar gets changed because the gravitational force of the planet sort of drags the signal, if you like. It's like if you've got a lighthouse, but it sometimes has to slow down because of the gravity of, something very big near it is pulling the beam so that it doesn't get to go around quite as fast as it should.
Yeah, strange analogy, but yeah, we'll go with that one. That's got to be a really weird planet, though.
Part of the reason why it's kind of not often listed, I guess, is the very first detection, and why it's not been the most successful detection mechanism that we have, is because these are crazy environments. We not even quite sure how these planets are there? Did they form after the supernova?
What even are you?
Did they get captured later on? Are they leftover bits of planets that used to be around the star? It's still sort of up for debate. But
yeah,
very weird objects.
Reminds me a little bit. Well, I watched Interstellar, the movie Interstellar, on the weekend again. I've seen it a couple of times, but my daughters hadn't seen it before, and it just reminded me of just how much of that film, from a physicist and astronomer point of view, is what. That's insane. Like, there's a planet going around a black hole, bunch of planets going around a black hole, and that's fine. Let's just go and land on it, and it's covered in water and big waves and stuff. No, I don't think so. If you're going to be next to an enormous black hole, I don't think it's going to look like that. Maybe that's just me. Anyway.
Your disbelief was not suspended enough.
It was not. I could not suspend my disbelief fast enough. Anyway, enough about that. And sorry for the spoiler on that one for anyone who hasn't seen it.
I think we've talked about Interstellar enough.
I think we have. I think people know our opinions of this film. What did you say? It was a great first half of a film.
Yeah.
Anyway.
And yeah, I guess finally more recently, do you remember when there was a big news announcement, and this is going back to 2008.
All the way back to 2008.
All the way back. Where we found prebiotic molecules in a different galaxy. It was in Starburst Galaxy, ARP 220.
Yeah, that does ring a bell. Yeah.
It was a big deal because this was kind of the idea that if you find prebiotic stuff, like precursors to life, then there's no reason to say that those things couldn't have come together and formed into sort of plants and animals. And
doesn't mean that they did, but finding those building blocks then allows you to, ponder the possibility that those building blocks could build something. And so that's a really important stepping stone along the line to, I don't know, maybe there's life out there somewhere. So that was that first time. That was Arecibo again. It's had a pretty good run of firsts, hasn't it?
It has. I mean, and what I sort of found, I thought, well, how am I going to sort of summarize all the research that Arecibo does? I mean, there's some nice little list of kind of the important discoveries, but it glosses over a little bit the thousands upon thousands of hours of research time that has produced really amazing stuff in so many diverse fields in radio astronomy, planetary science, etc. So I really didn't know how to kind of summarize that. And then I thought, actually, what I did was I got a bit nosy and I went and thought, I'll go and look at the observing program for Arecibo. I'll see what they've been up to most recently.
Before it all fell apart.
Yeah. So the last observations that Arecibo did was in August, before we had this cable breakage and everything stopped. So I thought, I'm just going to pick the last 3 observing proposals that were running on Arecibo, which were just running in the last sort of few hours before it was switched off.
Okay.
And let's just see what they are.
Sure.
Just for interest.
The very last ones.
And I was just fascinated by them. So the third to last one was a project which is called Completing the Palfar Galactic Plane Survey.
Right. And what's the Palfar Galactic Plane Survey when it's at?
So it's a big pulsar survey. So they're searching for new pulsars. This is a project led by people in Canada. And amazing. I didn't look too deep into the survey itself, but they've already discovered 190 new pulsars just from this survey.
Wow.
So that's pretty cool.
That's good. Right. And that's third.
That was third. Then the second to last project was the observation of repeating fast radio bursts in the disk by CHIME.
And fast radio bursts being a bit of a flavour of the month in astronomy, isn't it? Because
amazing, yeah.
It's still, there's still very little knowledge about what the hell these things are. What are fast radio bursts again? I mean, it's kind of in the name, isn't it? It's what's written on the tin. Yeah,
they're really, really bright, short signals that we get in our receivers from different astronomical locations. So they are astronomical in source, we're pretty sure. So they only last for something like a millisecond, but there's this huge power output in the radio. And most of them are just sort of single one-off events, and they just happen and then they're done. But there are a few that repeat. So semi-regularly or sort of, not quite regularly, but yeah. So I
love the way that you introduced that with, we're pretty sure that they're astronomical in nature. I mean, that just shows how cutting edge this is this astronomy? We're pretty sure it's out there and not down here or in the atmosphere or something, but we're going to put a little caveat on that. We're not 100% sure.
Well, they have been associated with astronomical sources, so that's a
Right.
good clue. They're not just coming from sort of random bits of sky.
What's the best guess at the moment? What do people think? Because there's a lot of energy, right?
Well, that's the thing. We just have no idea. It is really kind of just like, what?
What was that?
What was that? Something very highly energetic happening is all we've got so far.
Right. Well, that's exciting. So Arecibo was looking into those.
Yeah, well, I think that's something we can talk about a little bit more maybe in a future episode, because there was just one last month discovered in our own galaxy, which is very exciting.
Okay, write that up on your virtual whiteboard then, Emily.
Yep.
Fast radio bursts. I don't think we've done an episode on that. We've mentioned them, but I don't think we've done an episode.
They sound quite cool.
Yeah, let's do that. Okay. And what was number one?
Yeah, well, so that program was led by a team from the US, so that's quite nice. And then number one, which I actually found to be the most interesting for me personally. I'm sure all science is interesting, but this one really caught my attention.
But show your bias, that's fine.
The search for molecular gas and dual AGN using hydroxyl megamasers.
Okay, there's a lot to pull apart there. The search for what? Molecular gas?
Molecular gas, yeah.
And so that's as opposed to what?
Ionized gas or neutral gas. So, gas made of molecules. So you're looking for molecular gas. That means you're probably looking for areas where stars are going to form, star-forming regions.
Okay, so we're looking for star-forming regions. Where?
In dual AGN.
Dual AGN. So an AGN is an active galactic nucleus, which is a supermassive black hole that's feeding. How am I doing? Yep. Okay.
You're doing really well.
Dual AGN. Help me out here.
So these are sort of pairs of galaxies where one or both of them has an AGN.
Right. And they're interacting? They're colliding?
Probably. I didn't look into it huge detail, but yeah, I guess they must be having some kind of gravitational interaction.
Okay, so we've got looking for molecular gas, which might or might not be star-forming regions in dual AGN, so potentially interacting active galactic nuclei, galaxy, supermassive black hole things. What was the third part of this?
Using hydroxyl megamasers.
Which is what?
Right. Okay, let's go to the last bit first, a maser. Have you heard of a maser before?
Oh, I was thinking maze as in you find your way through to the exit type maze, corn maze, that kind of thing. Mega mazes. No, these are maze. Okay, fill me in. What's a what?
Well, a maser is actually pretty similar to what you are very familiar with, something, which is the laser.
Laser? Yeah, okay. So a laser is a light, like very, very highly correlated light source. So all the light is lining up its waves very, very carefully. So what's a maser?
Same thing, but instead of in the optical, it's in the microwave.
Oh, okay. So it's a laser, but you can't see it. It's microwaves.
Yeah. Actually,
right.
Fun fact, we discovered masers before we discovered lasers.
That's cool. Okay.
Yeah.
And so what's a mega maser then?
It's just a very powerful maser. So what happens is when you've got these hydroxyl regions, the region itself can create these masers, which are these kind of beams of correlated light that are in a specific frequency related to that molecule. And we can pick that up, and that's actually a fingerprint, if you like, that area of a galaxy is a star-forming area.
That's really cool. Okay, so yeah, I'm with you. I'd go that one. That would get the award, the gold medal for those three. Just such a shame that they were probably in the middle of doing all of that or gearing up to start it when the whole thing fell apart.
Yeah. And then most of these proposals came in only in March this year, so they're kind of new science that people are trying to do.
Sorry to all the researchers involved if you're listening.
Yeah. So that was led by a team from India. So I think it was just nice. And I scanned through sort of a dozen or so of these proposals, and it was truly international. People applying for time on Arecibo using lots of diverse groups doing very, very diverse different parts of science. It was pretty incredible. I was really a bit blown away by it all. And then I thought, you know what? This is one of the reasons why... I guess the NSF line is that Arecibo has reached the end of life, but a lot of the astronomers disagree. They were hang on, this is really cool.
We were using
stuff.
that. We were using that. You could have... Oh, it's too late. Oh, well. Now, Emily, you mentioned way back, probably half an hour or so ago in this podcast, you mentioned that Arecibo had been useful in another part of research, which is SETI, the search for extraterrestrial intelligence. And I seem to remember that there was a very important part of our history as a species in SETI, which actually had the name of the the dish involved, the Arecibo message. Tell us about Arecibo and SETI.
Yeah, so I guess broadly SETI's been sort of involved with radio astronomy since the beginning. SETI projects are generally privately funded. They're not tending to be publicly funded anymore. So the SETI at Home project is probably the most famous one, where people can offer up their computer time to trawl through data to see if there's any sort of weird signals in it. And a lot of that data still comes from, used to come from Arecibo.
Used to, up until recently.
It's just, it was data that was taken for normal astronomical purposes, and then the SETI sort of team would let's just have a quick look and see if we find anything interesting in there.
Because the idea being that, it's very unlikely that if we were to see some kind of signal from, life out there, it's very unlikely that it's going to come in the form of an email or something that is, here is a message to humanity written in the following way. It would be more likely to be something broadcast intentionally or otherwise out from an alien civilization out into the cosmos in the hope of finding something. And so we'd be just trawling through all of our, astronomical images or readings from the cosmos, looking for something out there. And that takes an enormous amount of computing power. So the SETI at Home thing was, look, if you give up a bit of your computer's processing cycles when you're not using them, you too can join the search. But government funding wasn't really a big part of this, because it's kind of difficult to convince the government, you should really pay for this really, really, really unlikely thing that we're looking for.
Yeah, there used to be government funding sort of back in the 60s, 70s, but that's pretty much, it's all moved to private enterprise now.
Yeah.
But you say, you're right in saying that it's very difficult to say if we could pick up something unless it was intentionally broadcast. And so one idea, which I guess was kind of floated by Carl Sagan, or at least he had very high, and actually Frank Drake as well, who both of whom I think we've talked about, in the 70s, was that actually let's just broadcast our own signal out there and see what's going to happen.
Yeah, why not?
There was, I guess, some controversy at the time whether we should be doing this and alerting people to our presence in the universe.
People or things. Yeah. Is this a sensible thing to do? What if we get a response and it's not friendly? Was that the idea?
Yeah, pretty much. But let's be honest, this was a very tongue-in-cheek exercise. What they did was they put together 1679 bits of information. So these are ones and zeros. Mm-hmm. They chose 1679 because it's a prime number, which is also a factor of two prime numbers. So those bits turned out to be a 23 by 73 pixel bitmap image. Mm-hmm. So this is kind of starting to date this a little bit.
It is a bit, yeah.
But the image was, it had a few numbers. It had some info about DNA, nucleotides, the double helix, kind of a little stick figure person made out of pixels, planets showing which one we were out on, on that. It was all kind of a bit cute. And then the very last, actually, I think now for me, the most poignant part of that is the very last image, which was a picture of Arecibo showing the dish.
That's right. Yes. Yeah. And that was that to show both where it came from, but also scale? Was it trying
to... the dish, they did have some information about how to scale the dish based on the wavelength that's being distributed. But yeah, it's just kind of, this is the dish that sent this message. And if you want to sort of imagine what that little pixelgram, if you like, is, if you sort of draw a arc, like a rainbow, just a single arc, and then have a capital M where the 2 points, the top points of the M touch the inside the arc.
Okay, yeah.
Then you've made a little symbol of Arecibo, which is quite cute.
Very sweet. Very sweet. Now, you said that this was kind of a bit tongue-in-cheek. So you're saying that this wasn't necessarily sent out into the cosmos. And by the way, this is using Arecibo's send feature, right? There's a beaming it out into the cosmos. And this is not with the intent of absolutely, well, someone's going to find this. This is more the intellectual exercise going through, all right, okay, let's say we had to send a message, or turning that around, let's say we had to look for a message. What are the sorts of things that we might be looking for? And so if you can figure out, well, what would unambiguously be a message as opposed to just random stuff, or, a periodic thing sent from a pulsar? Because that was, remember, when the first pulsar was discovered, it was called LGM-1 for Little Green Men.
Yeah.
1,
well,
because it was so regular. And that, again, tongue-in-cheek, because we don't really think this is aliens, but we don't know what it is. It's so regular. So if you discount regular things, because we know, like, pulsars, it's not going to be regular, then what would you send? And the notion of doing prime numbers, because it's pretty unlikely that you're going to find a pulsar that's going to be sending out a message which is a sequence of a product of 2 primes, or whatever it is, the sum of 2 primes. It's not going to be the product. That's not a prime number anymore. Sum of 2 primes. Like, that's really unlikely. So let's use prime numbers, because they should be universal. And then within that, what could you encode, in a relatively short or small amount of data? It's a really interesting, intellectual exercise to work that one out.
Yeah, it is quite fun. And of course, remember, this is the era of the Voyager spacecraft going out with their gold discs. And, we were thinking about contacting other civilizations in a very different way, I think, to how we think about it today. Today, it's sort of just like, oh, yeah, well, whatever, that's never going to happen. I think people in the sort of 60s, 70s really had this kind of idea of this, because so much development had taken place over the space race and so on, that we were on the verge of being part of a more universal community.
Yeah, it's amazing, isn't it? The universe was just opening up at that point. We'd just gone to the moon, or we were on our way to the moon, which is just the next step out. But at the same time, you've got radio astronomy really taking off, and astronomy in general, even within the previous few decades, showing us that our little world and our little solar system and our little galaxy is just one tiny part of this ludicrously vast, potentially infinite, cosmos of stuff. The notion of contacting other life must have just been incredibly powerful to society at that time, in a way which now we're just sort of, if it ever happens, then whatever.
Yeah. But if you do have some concerns about the Arecibo message being picked up, I mean, first of all, if I received that message, I would not know what to do with it. I would never be able to put it back into its bitmap pixelogram based on the binary sequence. I think I would just look at it and be like, okay, that's a bit of a blurb in the instrument. I better go check if there's pigeons in my telescope or something.
Although, again, I mean, it's this fascinating thing of we've just found this repeating signal, which it's a prime number. And I mean, have you read the book Contact? That was Sagan.
I have seen the film, which I was going to mention.
Yeah. So in the book and in the film, I'm assuming they go into the same detail. I haven't seen the film. You've seen the film. I've read the book. The message, like it's about, again, spoiler alert, message received from outer space. And the first level of that message is this notion of a repeating prime number. And there's something in this, but they are able to sort of, find other messages within the message and dig deeper and find other frequencies and so on. And there's enormous amounts of information in that one. It's more than just a pixelated picture of Arecibo, but it's a fascinating idea. Yeah.
But even if that doesn't convince you, if you think you would be, the kind of civilization that would decode it, the message was sent in the direction of a globular cluster called Messier 13,
right,
which is a globular cluster is a very sort of dense population of stars all in one location. You've got tens of thousands of stars in a very, very tiny bit of space. So I guess you're kind of upping your odds of being detected because you've got lots of stars there.
Sure, that makes sense. Yeah.
Whether globular clusters may not be the best environments for planets that we know now, but let's put that aside.
At the time, it seemed like a reasonable thing. If we're going to send this out, send it to where all the stars are. Yeah.
The only problem is Messier 13 is about 25,000 light years away.
Right. Okay. So 25,000 years from, let's call it, to all intents and purposes now. 25,000 years from now, then the signal will reach there. Good. Okay. It's quite a long time to wait.
Well, except it's not going to quite reach there. Oh. It's going to reach the place where Messier 13 was 25,000 years
ago.
Because
because everything's in motion, right? And so by the time it gets there, where will that globular cluster be? Will it sort of move completely?
Somewhere else.
Oh, poo. Surely they thought of that. Like these were.
I think
these
they
were
thought it. And this
intelligent
is why
people.
you can tell this is all just a little bit of fun.
Is this a little bit like us in episode 50 of Syzygy beaming our podcast out into the stars? Where did we send that to? Betelgeuse, wasn't it?
Betelgeuse, yeah.
Yeah. So we're not necessarily expecting that episode 50 of Syzygy is actually going to reach Betelgeuse.
No, I think Betelgeuse has got bigger problems at the moment anyway.
I think it probably does, actually. We should come back to that at some point. Well, as an intellectual exercise, the Arecibo message was a lot of fun, but we're not necessarily... I mean, how long was it broadcast for?
That's a good question. I'm not quite sure. It wouldn't have been very long.
Wouldn't have been terribly long. And so it's sort of the astronomical SETI equivalent of, in those heist movies where they're trying to break into the bank and you see from the point of view of the security guard and all of the security cameras showing up on the monitors in the security guard's office. And just at that moment, the dude decides to go and make himself a cup of coffee is when the bank robbers sneak across in front of the security camera and make their way through to the vault. It's the equivalent of that if we sent the Arecibo message off towards this globular cluster for a short period of time, and they, the alien life up there in the globular cluster happened to be not looking in our direction for that short period of time, then the whole thing didn't work. They missed the message.
Well, it's even worse than that because you've got something called the inverse square law.
Yeah. Just remind our listeners the inverse square law.
So the inverse square law is that your signal gets fainter the further away it gets from you as a fraction of the square of the distance.
Right. So if you double the distance, you divide the strength of that signal by 4. If you multiply the distance by 10, then it's a factor of 100 smaller.
Yeah.
And so that adds up a lot.
So not very powerful for our sensors, but not very powerful. I mean, Arecibo struggled to reach Saturn with its radar.
So it could bounce radar off an asteroid and get an image back, but getting to a whole other globular cluster of stars, maybe not. Maybe not.
Yeah, the signal's going to be so weak by that point, it's just going to be noise.
So in 25,000 years, plus another 25 at the most, like at its fastest for a signal to get back to us, we probably shouldn't really be holding our breath for a response on that one.
I wouldn't be, no.
No. Okay. All right. Well, let's leave SETI behind then. That's a fun part of Arecibo's history, but let's move on. So, Emily, can you sort of help us to sum this one up? It's a sad end of an era for astronomy. What would you say made Arecibo so special? What was the big deal? What are you going to miss most?
Well, I guess there's lots of ways to look at it. I guess the first way you can think about Arecibo being special is just from the scientific perspective. I mean, we talked about lots of the discoveries. It was big. It was the second largest single aperture radio receiver in the world. The largest is now something called FAST, which is the 500-meter telescope, aperture spherical telescope in China.
Which is, let's make no bones about it, that's really big. This one was 300 and something. This is 500, which is really enormous.
Yeah.
I'm assuming it's not made out of concrete either.
No,
right.
It's actually built in a very similar model to Arecibo. Mm-hmm. Same sort of sinkhole process as well.
Yeah. Hey, I've just had a thought, Emily, really quickly. If this thing is built into the side of a mount or on top of it's built into the ground, right? How do you steer it? Like, it's rotating with the Earth. It's not pointing in the same direction all the time. So how do you keep looking at the same part of the sky? How does that work?
That's actually a really good question. It's a very amazing technological solution. So if you just took a normal sort of telescope and built it into a concave sort of shape, then you just have to wait for what you wanted to see to come up above you, right? To come into your field of view.
Yeah, and then really quickly, there it is. No, we've missed it again. Okay, we've got to wait for it to go around the entire day again. And that's really, really inefficient.
Yeah, but what you can do quite cleverly is you can do what we call beam steering with radio telescopes, which is where you sort of move the receiver around the dish such that you've got, with Arecibo, I think it was something like a 40-degree cone that you could observe close to the zenith, so close to straight up.
Okay. So the radio waves are coming down basically parallel because they're coming from so far away. They're effectively parallel. They're bouncing off the dish, but of course they can be bouncing off from all sorts of different angles. And because the dish is nice and big and curved, you can sort of find across the top of the dish, You can sort of move your focal point in order to steer, so that as you move across the sky, you're able to stay in focus with the bit that you're looking at. Is that the idea?
Yeah, kind of. It's actually to do with timing as well of your signal. So if you imagine if you had two sides of the dish, then you would receive, if you were looking straight up, you would receive the signal from straight up at exactly the same time from those two sides of the dish. What you can do with beam steering is actually delay the signal from one side of the dish, and that sort of tilts the whole beam over.
Right.
And in a slight direction.
Right. So did that enormous 300-ton bit up above the receiver, up above the dish itself, did that move, or was it all about the timing and the electronics?
I think it could move depending, like when it was needed for different sort of servicing and so on, but broadly it stayed where it was. Right. But you sort of pointed different bits in different parts of the dish, and then you could kind of use this beam steering to get around as well.
Right. Very clever, very clever. Anyway, that was getting off topic. We were talking about the largest one, which is 500 meters. Okay, so it was one of the two largest.
Yeah, so it was definitely one of the big ones. It transmits, and as we mentioned, it was one of only two, and now it's, there's only one in the world that does this. And it was actually much shorter wavelength than, for example, FAST is the 500 meter one. So Arecibo could go down to 3 centimeters in radio waves, microwaves, whereas FAST can only go down to about 10. And there's just different astronomy that you can do with those different wavelengths.
Sure. So we've really lost an important part of our astronomical infrastructure.
Yeah, but then I think what's interesting about Arecibo is kind of the human connection, because if I think about, so when I was a student at university, I remember learning about radio telescopes, and it was just, it was the classic example of this is a giant dish radio telescope. It's the biggest in the world. It was at the time. And you saw all these pictures of it, and it was just kind of this amazing thing. So even though I've never been there or even been involved in any research from Arecibo, it's always kind of one of these things that you just knew. It was just one of, that's the big radio dish in Puerto Rico. That's really cool.
It's been there so long. 57 years.
And so many people have seen it in films as well, because here we go. We got the 3 big ones, or at least 2 of them are big. I've not seen the third. In the 1990s, apparently, we loved Arecibo.
Yeah, okay.
1995, we had GoldenEye.
Oh, okay. I don't remember. I'm trying to remember. It's a Bond film, right?
Yep. The baddie falls in the dish. Oh, I might have spoiled the ending there.
Look, if a 1995 James Bond film is a spoiler, then I'm sorry. You just need to watch more films.
There was another one in 1995 called Species. It's not a film I've seen, but...
Oh, yeah, I vaguely remember that one coming out. I don't think I saw it, but it was aliens stuff, yeah.
Not surprisingly.
Mm-hmm.
And of course, the 1997 film Contact.
Yes.
Huge film.
Yeah, as we were just talking before. Yeah.
So, there's a lot of public sort of recognition of the dish, I think.
Iconic in both scientific and, popular culture. It was a big one in all senses.
Yeah. And then if you think about where it is, Puerto Rico is not really famous for a huge amount of big science apart from Arecibo, right?
No, that's right. And
it's a small island. It's got, this amazing research facility that provides so much, I guess, not only economic impact and science impact on the island, but a huge amount of pride for the community to have this amazing instrument.
Is it a bit like all the telescopes, up on top of the mountains on the plateaus in Chile? That Chile's not known internationally for its scientific output, but it does have these amazing facilities, the VLT and so on, the Very Large Telescope, and all of those amazing things up on top of the mountains there. And that's presumably because that's a really good place to put a bunch of telescopes, a bit like up on top of the mountains in Hawaii. But in terms of Chile's scientific prowess, that's a really good one for them to presumably rally behind. Is it a bit the same for Puerto Rico?
Well, yeah, and that's what's driven a lot of Chilean astronomers and Chilean scientific research institutes. And so, Chile is a big player, I think, just as a nation now in the astronomical community. I would imagine largely down to the investment that's gone on to putting these kind of facilities. And the same is true for Puerto Rico, right? You need a lot of people to run a big telescope.
Yeah, and it's investing in that kind of infrastructure locally can have a huge impact on what people, they see it around them. This becomes, you would hope, when you set something like this up, something of a bit of national pride and something which captures the local attention as well as the international attention. So that can have a really positive flow-on effect.
Yeah. So, I mean, there's a Twitter account, which I'm going to mention, and you should definitely go and have, or hashtag rather, you should go and have a look at it because it's really lovely. And it's a hashtag, what Arecibo means to me, or one word. I don't know if you had a chance to look through some of this.
I did have a bit of a look at it, although it made me smile because when you first sent it to me, I read the hashtag as what Arecibo meanstone. What Arecibo means. I don't know what Arecibo means to. Oh, what Arecibo means to me. Sorry, it took me a minute. Yeah.
But there's some charming stories in there. I mean, there's a story from a PhD student how using Arecibo gave her the confidence to shed what we call first generation baggage. That means like first generation involved in sort of academia in a family. How to get past those kind of imposter syndrome feelings that you have. There's stories of people or their parents taking them up as kids and saying, look, this is what is possible with human endeavor. This is what we are capable of. Like, it's
one of those grand things of science. One of those things that you can go and look at and point at and go, look what we can do when we put our heads together. It's truly iconic. And I can see why the destruction, the end of life for an instrument like this is going to lead to such a huge outpouring of emotion.
Yeah.
Both within astronomy and broadly across the world. It's got front page headlines.
Well, because it just never happens, right? When was the last time you saw the destruction so dramatically of any enormous research facility, let alone an enormous telescope?
I can't think of one. I can't think of an example. It'd be like the Hubble Space Telescope, crashing down into the Australian desert somewhere, not bringing any samples with it.
In some ways, space telescopes, we know when we put them up that they're not going to live forever. I mean, Hubble is living forever, which is amazing. But, we know things like Herschel and so on have a finite lifetime. Kepler had a finite lifetime. And, when they stopped, it was sad and we were, emotive then, but you knew from the beginning when you have a ground-based facility like this that's been there for the better part of 60 years, you just don't expect it to go. You don't build these things to just fall apart. The only other even similar example I can think of was actually in Australia in Canberra. And the observatory there, they had a bushfire that took out some of the telescopes. And that was heartbreaking for the astronomers working there at the time.
I went up there a couple of years after that and took a wander around the telescope site. And it was pretty powerful because there were these sort of, burnt out hulks of buildings, including some really old telescopes. And that was pretty heartbreaking as well.
And maybe I'm going a little bit too far here, but in astronomy, I sort of feel that also we use our stuff for a very long time, right? We built Arecibo, we're using it, 60 years later, and as a modern breaking research facility.
Yeah, cutting edge
stuff. Would that happen
stuff.
in particle physics, Chris?
No, I mean, you upgrade as much as you possibly can, but what tends to happen in particle physics is, no, we need bigger. The particle accelerators of 57 years ago would be laughable by modern standards. There's no way. I mean, it wouldn't be that they're not useful anymore, just that they wouldn't be used for, like, you wouldn't find the Higgs boson in a 57-year-old particle accelerator. The 57-year-old particle accelerator might become the first stage of your new particle accelerator. It's just to get things warmed up,
Yeah.
So it's not an upgrade so much as a complete replacement where the old becomes, if you're lucky, just one component of the new. And that wasn't the case for Arecibo. It presumably got a lot of equipment upgrades and so on, but it was still the big dish with the three towers and the big 300-ton thing sitting in the middle of it.
And fundamentally operating in the same way it was when it was built. Yeah. So
right. It's an old friend.
It's interesting that you can do that sort of comparison where if anyone else in physics or science can pull out a 60-year-old piece of kit and say, hey, I can make some new discoveries on that, I think that's pretty rare.
Well, that brings us to the end of what has been a particularly melancholy episode. I don't remember if we've had a sad episode of Syzygy before. Emily, do you?
Not sad because of things that were beyond our control, at least.
Yeah. No, I mean, we've had exciting, we've had intriguing, surprising, shocking, but I don't remember ever feeling sort of, I'm going to miss that telescope. Oh, well, I hope listening out there in listener land. Look, if you want to get in touch with us and send us through your memories of Arecibo, or just express your feelings of sadness and loss, or even just sort of fond-hearted memories, then there are ways that you can get in touch with us. Emily, name at least one.
Well, if once you've finished feeling very tearful reading through the hashtag what Arecibo means to me,
then, once you've figured out what that hashtag is, yeah,
then you can tweet us again on @SyzygyPod. That's at SYZYGYPOD.
That's right, and that is a name that we use in other places as well. We're on the Instagrams @SyzygyPod. We're on Facebook. You can go and search for the Syzygy podcast, SyzygyPod, on there. And you can also go to our website, syzygy.fm, where you can find all of our shows, all of our past shows and show notes, and our great wall of thanks to all of our supporters, particularly through patreon.com. You can become a patron of the show over at patreon.com/SyzygyPod. You can find, as I said, all of our past shows. You can find a contact form where you can send us through a message. And in particular, if you've got any questions or ideas for a future show, then we'll have a look at it. You never know. We might base an entire episode of the podcast around your thoughts. I think, Emily, we've actually got a couple of those sitting there waiting to be looked at. I seem to remember over the last couple of months.
I've got some from the summer that we need to go back to,
yeah,
because I feel terrible because some of them are done by some of my research colleagues. I haven't got around to them yet.
Come on, Emily, what have you been doing with your time? I mean, those of you who are, listeners of the show may have noticed that things have slowed down a little bit here at Syzygy HQ. And look, it's 2020. We don't need to offer any excuses. It's just the year that has been. We are continuing the show. We're not giving up. It's just been a little bit slower than we thought. But we are going to keep going. We are continuing. The next episode of the show, I'm pretty sure, will involve me chatting to Emily on the other side of the world, maybe in a quarantine hotel somewhere around Auckland. You never know. In the meantime, keep listening, spread the word of the show, tell everyone that you know that you think might be interested in a podcast about astronomy, tell them to tune in. Otherwise, we will catch up with you, I don't know, in a week, sometime towards Christmas, maybe towards the new year. We'll see how we go.
We'll see if 2020 has got any other shocks for us yet.
Exactly. No, don't, Emily. God, don't say that. That's an appalling thing to say. No more shocks for 2020. Emily, I'll catch up with you sometime soon. See you later, everybody.
See you later.
No more shocks for 2020. Please, God. I couldn't take it. I just couldn't take it.
I don't know. At what point do you start? I'll say that what point do you start to become numb? But then I was really sad about the telescope, so I guess not.
Yeah, exactly.
That's
exactly.
Good.
Careful what you say, because it could get, there's still a couple of weeks left. There's all sorts of stuff that could happen.